Pre-calculus on-ramps. This will be the first of several videos that we're going to do to finish up the 5th unit, which is also the final unit for the UT OnRamps pre-calculus curriculum that I'm supposed to be teaching for the rest of the year. We had 2 more units. One of them was going to be tested by UT Unit 6. Unit 7 was an extra unit that was not going to be tested by UT no matter what, but it was there just in case we finished early and we needed some extra stuff to teach. And it's not necessary to go over that stuff. But because of the coronavirus situation and their response to it, they decided to cut off the course at the end of Unit 5. I've explained earlier, and you probably already gotten newsletters from UT, but for pre-calculus specifically, we'll be needing to test Unit 5, and that's going to be it for new content. You'll have another test afterwards, but it's going to be the final. And from what I understand, the final is going to contain material only from Units 4A, 4B, and Unit 5. So trigonometry, rational functions, limits, and derivatives. And the rational functions, limits, and derivatives are things that we're going to be seeing in Unit 5. Rational functions we've already finished up. You had 2 homework assignments, but I'm going to be going over some extra notes just in case, since we will be needing to review the material anyway, so I'm going to want some video stuff over that. And then if I have time later on after we finish all the Unit 5 stuff, before we start review for the final exam, I will be re-recording lessons for Unit 4, so that way we can also have some more material to review. So what we're going over in this particular video is the stuff on rational functions. It's theoretical stuff. This is notes that I normally go over with my dual enrollment class, the STC one, or my pre-AP course. This is Chapter 3 in that textbook. This is Section 3.5, specifically just on rational functions only. The majority of the chapter is over polynomial functions. This is the last section in that chapter, and it's only one section over rational functions. So I'm skipping around. I'm not going to start from the very, very beginning. I'm starting with the 5th example, which I don't remember how many examples there are, 9, 10. But we're starting at example 5 and covering the graphing stuff. So we'll look at example 5 right away. I'll even skip this stuff. So for example 5, they're going to ask us to graph this particular function, f of x. F of x is equal to x minus 2 over x squared minus x minus 6. And they went over a set of steps here, and maybe I should go over those steps. The very, very first thing you're going to want to find are any horizontal, actually no, not horizontal, vertical asymptotes. Then we find any other type of asymptotes, which those include horizontal or oblique is the word that we use for these. Slanted asymptotes would be another one. But the only types of asymptotes that we're going to be interested in a pre-calculus course are linear asymptotes. There are other nonlinear types of asymptotes, but we're not going to be going over any of those. So it's either a vertical, horizontal, or something else, which we call oblique. So for this particular function, to find the vertical asymptotes, which I'll just abbreviate, you set the denominator equal to 0. So in this case, it's a polynomial, x squared minus x minus 6. We're setting this equal to 0, and we like to solve for x. Now, in order to solve for x in this situation, we notice that we have a quadratic equation that requires solving for x. And there's a number of techniques that we can employ. And usually the one that I fall back on, if I see that there's a middle term, an x term, if there was just an x squared term and a constant term, you can solve by isolating the x squared term and then square rooting both sides to solve for x, and you'd be done with that. You'd have 2 numbers that differ by a plus or minus sign, or something of that sort. There'd be a plus minus in there somewhere. But if I see that there's a middle x term, that kind of messes that situation up. Then the first thing I'd like to go with is maybe factoring. Factoring would probably be the easiest. So what we do is we look at the first coefficient, the leading coefficient, which in this case it's an implied 1, and then the constant term, which is negative 6. You multiply those two, and we get a product of negative 6. So we also keep track of the middle coefficient. The middle coefficient is negative 1. This is going to be the sum. That's supposed to be an s. So I have 2 numbers that I'm looking for that I'd like to split this quadratic polynomial using these numbers And these two numbers, hypothetically, they're supposed to have a product of -6 and a sum of -1. So two numbers whose product is -6 and whose sum is -1. So right away I'm thinking of the numbers 2 and 3. Maybe, maybe not. So if I take 2 times 3, I get 6, and if I maybe subtract them in a certain order, I can get -1. And that could be achieved by maybe moving the negative in front of the 3. 2 times -3 is -6, so that works. 2 minus 3 is -1, so I like these numbers. So what I'm going to do, 0 must equal 2. There's the long way to do this, if we forgot. X squared, instead of minus x, you're going to say that that's plus 2x, minus 3x, and then minus 1. You split up that middle term into two terms. So we make that middle term 2 so that we have a set of, so that way I have an even number of terms. So there's 4 total terms now instead of 3. And the reason why we want even terms is I can group them by 2's. And if you chose your numbers correctly, when you group by 2's, and then you factor each of those groups of 2 individually, in this case the first one has a GCF of x. This is x times x plus 2. This one has a GCF of, well, -1. There's really just a negative sign that they have in common. Oh, and I did this wrong, didn't I? I'm probably going to have to edit that out. But I don't know why I wrote a -1 there. That should be a -6. Yeah, so that wasn't going to work out. They have now they have a GCF other than -1. They have a GCF of -3. X plus 2, and that's going to equal to 0. So if we did this right, which in this case I didn't do that right, I didn't copy down the -6 properly. But if you chose those numbers correctly and you copy everything down correctly, you notice that there's a common factor still. That's the binomial x plus 2. We factor this out and we're left with x minus 3. And that's completely factored in this case, since both of those binomials are linear in the x variable. And by linear I mean degree of 1. So it's just x, not x squared, x cubed, or anything like that. So what we do now is we solve for x using what we call the zero factor property. We have the product of two numbers. It doesn't look like two numbers because that might look a little complicated, but x is a number, theoretically. X plus 2 will still be a number. X minus 3 is also still a number. Two numbers, when I multiply them, are supposed to be equal to 0, and that only happens when either of those two numbers, either x plus 2 or x minus 3, are both equal to 0. So one of those must be the case, or both must be the case, in order for us to get a product of 0. So x plus 2 is equal to 0. That implies that x equals -2. And in this case, x minus 3 is equal to 0 implies that x must equal to 3. So here what we've done is we've deduced that the only values that make the denominator equal to 0, because what we were doing is we were setting the denominator of this bigger function equal to 0. So what this means is these are the only two numbers that'll make the denominator equal to 0. So these are my candidates for vertical asymptotes. X equals to -2 and x equals to 3. So then what we do is we check. We set the numerator equal to 0, and this one implies that x equals to 2 if I set that equal to 0. If neither of these match with the numerator zeros, then these are both vertical asymptotes. So I'm going to box those. Now we saw earlier that if the numerator and denominators share zeros, you don't get asymptotes, instead you get holes. So I have two vertical asymptotes, which I will go ahead and start the graph up. There's one at -2, so I'll draw a red vertical dotted line. And the other one happens at 3. Now one thing we saw earlier as well, so I'm going to rewrite this function, f of x, like this, in terms of only linear factors, x minus 2 divided by x plus 2, x minus 3. So that's the bottom factorized. So in this case, we check all of those linear factors. And in the denominator, if those factors on the bottom are linear, in this case, we check all our factors, not the linear factors, all factors. Because sometimes you might have a repeating factor that has a quadratic or a power of 2 on it. All of these have power 1. So they're all linear factors. So the ones on the bottom, if those factors are linear, then what we get is around those asymptotes, we have this opposing set of directions. So same thing happens here. Something like this, where this goes up, and then this comes from the bottom. It goes like that. So then on either side of the one particular asymptote, you're going to have those, the end behavior is going to be completely opposite. So one's going to be pointing up, one's going to be pointing down. Now if those were quadratic factors, or if they had an even power, not just quadratic, power of 2, power of 4, power of 6, and so on, they would be pointing in the same direction, both up or both down. That's not the case in this situation because all of those are linear factors, odd degrees. Okay, so what next? I want to find out if there are any horizontal asymptotes. Now the way to find out horizontal asymptotes, you look at the function itself and you analyze the degree on the top and on the bottom. So if I were to multiply back out the original functions for the numerator and the denominator, and you check the degree, this has a degree 1. And the bottom is a degree 2 polynomial. Earlier we said it was quadratic. We factored it into 2 linear factors. It's a degree 2 polynomial. So then we compare the degrees, top and bottom. If the degree on the bottom, the denominator, is larger than the degree on the top, then we are always going to have a horizontal asymptote of y equals to 0, x-axis. Now unless the denominator function contains a factor of x by itself. Because if we had an x on the bottom, then we don't have an asymptote. We'd have a whole situation, a discontinuity there. Okay, so then my horizontal asymptote is the x-axis. So I'm drawing another dotted line. In this case, x-axis. So those are both of the asymptotes. What's our next step? Then we want to figure out some points along the way. So there's some easy points. So we're going to try to plot points. And I'm not just going to pick some arbitrary x or y coordinates to do that. What we want to do is maybe look for intercepts, because those are easier to find. So we can try looking at X intercepts. And this might look a little unorganized the way that I'm writing this. I kind of took up a lot of space already solving for the vertical asymptote locations. So the X intercepts are when f of x equal to 0. So we want the x coordinates for when f of x is equal to 0. So what we do is we set that function equal to 0. So 0 is equal to x minus 2 over x squared minus x minus 6. So we're assuming denominator is not equal to 0, so we're staying away from the asymptotes. We're talking about everywhere else. This is a fraction, and fractions are only equal to 0 if the numerator is equal to 0, and as long as the denominator is not equal to 0. So this implies x minus 2 is equal to 0. So again, fractions are only equal to 0 when the top is equal to 0 and the bottom is not. So we're disregarding the bottom, and it's only when the numerator is equal to 0. This is x equals to 2. We kind of already solved that earlier. I was comparing the zeros of the numerator and the denominator. It turns out that the zeros of the numerator are x intercepts, as long as they're not zeros of the denominator. Otherwise, they wouldn't be x intercepts. There would be the function would be undefined at that place. So the only x intercept I see is x equals to 2, and I'm going to zoom in on this graph. So I have one x intercept at x equals to 2, which I'll draw in black. And that is the only time that this thing crosses the x-axis. Now we had discussed earlier in class, is this not supposed to happen? We're not supposed to cross x intercepts, which that's an incorrect assumption. We can cross x intercepts. Asymptotes. So we just crossed a horizontal asymptote. And there might be some sort of a rule that you were taught earlier that we can't do that. That would be a false rule. We can cross asymptotes. Asymptotes are just end behavior, what the graph is doing at infinity. So the further and further and further we get away from the origin, what's the function tending towards? And it's tending towards a line. But no, in between locally we can cross the asymptotes no problem. So x equals 2 is the only x-intercept. So good, I have a point. I need a ton more points. So we're going to look for another intercept. The other type that we have would be the y-intercept. And I'm not going to put plural on that because there's only ever one y-intercept, otherwise this wouldn't be a function. So my y-intercept is when we plug in 0 into the function. So in this case, that's 0 minus 2 over 0 squared minus 0 minus 6. So I'm plugging in a 0 anywhere I see an x in the original definition of f of x. And then we simplify. So then we get 1/3 if you simplify that. So on the y-axis, this graph is supposed to cross 1/3, which is somewhere down here. And I'm kind of already seeing what this thing's going to do. So I'm imagining this graph will do something like this, tend towards the vertical asymptote on that side, and then do this, tend towards the vertical asymptote on this side. And we can check other points in between. So let's say we can plug in -1 to see what the y-coordinate is there, and I might be off vertically, but the point is I'm going to be above the x-axis. It's going to be a positive number. So we'll check. Let's try f of -1. Now what I'm going to do to make this shorter is do this on my calculator on the side. Now I can't show a calculator here. I have my physical one. I'd have to stop recording and then re-record with the calculator app on there. So it's kind of a limitation that I have on recording. Alright, my calculator gives me 3/4 when x is -1. So I'm a little off with the way that I drew this. So 3/4 is here somewhere. So that's going to rise up a little bit to as we're going to the left. Otherwise it's decreasing, because decreasing going from left to right. So if I type in, because I can't type in -2, if I type in -2, it's going to give me an undefined, or it's going to complain. So let's say -1.5. So between -2 and -1, I get 1.56-ish, so somewhere around here. And you kind of get the idea. The closer we're going to get to -2, the higher up this is going to go. So we can also check f of 1 should be really, really close to 0, but not quite 0 just yet. And it's still going to be positive, 1/6. So at 0, not at 0, sorry, at x equals to 1, 1/6. When we plug in 2, we should get 0. Let's say if I plug in 2.5, 2.5, which I'm doing this in the calculator that I'm not showing. I'm getting -0.222, and it keeps on going. So yeah, and the closer I get to 3, let's say 2.9. So if I plug in x equals to 2.9, I'm getting -1.837-ish. And the idea is the closer you get to 3, the faster that's going to blow up towards -infinity. So that's what the middle looks like, in between -2 and +3, the two asymptotes, the vertical asymptotes. So then what else am I doing? Since there's a couple of things I can go ahead and do. Since I know that that's the only place that this is going to cross the x-axis, and this has asymptotic behavior, we're going to see one of 4 different things. Either this guy is pointing down this way, or maybe it's pointing up. So it's one of 2 things on the left. On the right, either up or it's down. So in terms of combinations, that's 4 different ways that can go. Both up, both down, one up, one down, or the other one down, and the other one up, in the reverse order. So it's one of those situations. So I think I have enough to figure out which of these it's going to be. Now, concentrate on x equals -2. We had said earlier, since that was a linear 0 at that asymptote, these 2 ends should be pointing in opposite directions with respect to the asymptote. So that guy's going to be pointing down. Now, using the same argument for the one at x equals to 3, this one should be pointing up when approaching +3. So this is what the graph is going to look like. So I can stop there, and that's going to be good enough, or I can plot a few points just to prove my point, and maybe make the graph look a little bit nicer. So I'm going to go ahead and plot a couple of other points just to see what we have. So what I'm going to do is I'm going to take my calculator again, and let's say I'm plugging in x equals -3. And if I plug in x equals -3, I get -0.8333 something. So at -3, -0.83 something something, so that's close to -1, but not quite -1. If I take that to -4, x equals -4, we get -0.4285 something. x equals -5, negative 0.292. And you kind of get the idea. If I get closer to -2, let's say, so negative 2.5, negative 1.636, so somewhere around here, and you kind of already see the curve that it's shaping out to be. This is going to look something like this. And then on this other side over here as well, it's going to converge towards the x-axis. So let's do it on the other side. So close to 3, but on the right side of 3. So to the right of 3. So let's say x equals to 3.5, positive 3.5, and I get 0.5454545 and so on. That's around here. If I plug in x equals to 4, 0.33333, so that's 1/3. If I plug in 5, 0.214. So you kind of get the idea. This is slowly going towards 0. And this one has a bit of a, that's decreasing from the left, but from the right it's increasing. So eventually it's going to blow up towards positive infinity. And that's what this graph looks like. So that's good enough. So several takeaways. You want to find the horizontal asymptotes. That's going to be the, depends on the degree of both the numerator and the denominator functions. You want to find the vertical asymptotes, you set the denominator equal to 0. You set the numerator equal to 0 as well, and vertical asymptotes happen wherever the bottom is 0 and the top is not. X intercepts are where the numerator is equal to 0, but the denominator is not equal to 0. And then the y-intercept just happens when we set x equal to 0. And then you just plot points. So that's the easiest example. We'll make them a little tougher, where the vertical and horizontal asymptotes might be a little tougher to find. So let's say, for example, 6. This is going to be different than example 5 because if you check, numerator and denominator functions have the same degree. They're both linear polynomials. So then I throw that out the window. I throw the idea where we have the x-axis equaling to the horizontal asymptote, and that'll get thrown out the window. So we'll keep on going in the same order though. Are there vertical asymptotes? F of x is 4x minus 2 over x plus 1. Vertical asymptotes will happen when x plus 1 equals to 0 and 4x minus 2 does not. So I'm going to write 4x minus 2 equals to 0 as well. So I'm going to solve both. So the denominator is 0 when x equals to -1. And the numerator is 0 when x equals to 1/2, it looks like. Since those two don't match, then this is my vertical asymptote. X equal to -1. So we'll draw a vertical asymptote at x equals to -1. And that was way easier than the previous one. So we definitely have a vertical asymptote at -1. It's a linear polynomial. The vertical asymptote there is linear, so I'll call it linear since it has a degree of 1. It came from a polynomial x plus 1. So then it's going to have the opposite direction on those two curves on either side. Okay, so we got to do some more work. Horizontal asymptote. You check the degree. They're both degree 1. So I'm going to say degree equals 1. Degree equals 1. They have the same degree. So what we saw earlier in class several weeks back, if the degrees were the same, top and bottom, then what you do is you take the ratio of the leading coefficients. You set y equal to that ratio, and that's going to correspond to your horizontal asymptote. So there will be a horizontal asymptote if the degrees match. In this case they do, so horizontal asymptote. And you're going to set y equal to the ratio of the leading coefficients. What are the leading coefficients? On top it's 4, on bottom it's 1. 4x minus 2, 1x plus 1. So the 1 in front here that we don't see, that's the leading coefficient, 1. So it's 4 over 1, and you divide those two numbers, in this case 4. So then I'll draw that. Y is equal to 4. This is horizontal. It's going to cross the y-axis at 4, the vertical line that is, or the horizontal line that is. Not the function. The function will not cross there. And those are my two asymptotes. So at this point, all we have left is to plot a few more points, and we're going to be done. So I had said earlier, it's going to be one of these two situations. One pointing up, the other pointing down, or the other one just in the reverse order. The left one down, the right one up, or the left one up, the right one down. One of those two situations. So we plot points, and there are some really easy points to plot. Let's try X Intercepts first. And the X Intercepts occur when f of x is equal to 0. In this case, you set the denominator equal to 0, and we've already done that. Or not the denominator, sorry. You set the numerator equal to 0, solve for x, and we've already done that. X equals to 1/2. And I'm good to box that as an x-intercept, or to use that as an x-intercept, as long as that's not a 0 of the denominator, which it's not. The only 0 of the denominator is -1, so then we plot that 1/2 at 0, when y is equal to 0. So 1/2, 0, somewhere around here. And that's the only place where that's going to cross the x-axis. So I'm guessing this is pointing down on the left side of -1, which we can plot a few more points to verify, but I'm not going to. I already trust that that's what it's going to look like. Y-intercept. I'm guessing the y-intercept is negative somewhere down here. So it's not going to happen to the left of the vertical asymptote. It's happening to the right of the vertical asymptote. So we can check. So like I said, I was going to not plot any more points, but I'm obviously going to plot the y-intercept. So y-intercept happens when x is 0. So we want f of 0. That is -2/1, which is -2. So that should have crossed at -2. Looks like it kind of does. I'll go with that. Okay, the only other thing left is maybe to plot some more points up at the top left. So let's talk about points to the left of -1. See if I can plot any there. Let's say f of -2 to start off with. And for this, I'm going to want to use my calculator. Now the result when I plug in x equals -2 is +10. So I have a y coordinate all the way up over here. And let's see, we can go with some more points. -3, I get 7. So -3, we get 7. Okay, so we can keep on going. Let's say -7. Just to, oh, -7 is a nice whole number. It gives me 5. So -7 would be 5. That's about as much as I'm going to plot. So the curve does something like this. It's going to keep on dipping down that way. And that's what that's going to look like. So that's good enough for the graph itself. But I'm not really done talking about example 6 because there's another way that we could do this. Now if you understand the parent graph, and it's supposed to say the word parent. This one has a parent graph. F of x is equal to 1/x. We call that the reciprocal function. So the graph of that thing, if I draw the x and y axes, one pointing up, the other one pointing down. It has a vertical asymptote at 0 and a horizontal asymptote at 0. So x-axis is the horizontal, y-axis is the vertical asymptote. This is a shifted version, shifted up and left of this original parent graph. And not only that, I think it's scaled a bit. And scaled by how much, I'm not entirely sure. But the way that I can show this is that you can actually perform the division of 4x minus 2 over x plus 1. And I'm going to do that long ways. So we're dividing 4x minus 2 by x plus 1. So in order to make those first terms match, I'm multiplying by 4. And that 4 is expected. So that's 4x plus 4. And if I compare the two, we get a difference of -6. Do we? Yeah, we get a difference of -6. So then, To rewrite f of x as a result, actually I already have f of x up here. Because of the result of the division, I'm going to say that this is 4 minus 6 over x plus 1. So you'll notice that is a scaled or a dilated, this is a vertical stretch of a factor of 6. We have a reflection about the x-axis, and then we have a horizontal and vertical shift. The vertical shift is a positive 4. The horizontal shift is a negative 1. So there are the negative 1 and 4 that we have on the graph here. Asymptote was at negative 1, and that's where that shows, the negative 1. And then the horizontal asymptote was at positive 4. So this is the horizontal asymptote. That plus 1 there corresponds to an x equals negative 1. That's the vertical asymptote. This is a reflection. And that reflection just means that this was, the left is pointing up and the right is pointing down, whereas on the parent graph, left is pointing down, right is pointing up. And that scaling by a factor of 6, well, I can't really see that obviously, but it's going to be 6 times as wide vertically compared to the original parent graph. So that I want you guys to keep in mind. Division a lot of the times helps us reveal certain characteristics of the graph, and that's going to help us in the next example. So we'll go ahead and move on to the next example. Or maybe this is not going to help us in this example. I think I'm going to go ahead and skip this one for now, because I want to move on to the one where that does help. So we'll look at example 8. So I'm only going to want to go over example 8, and I think there's an example 9, and that's it. Now there's an applications problem 10, and that's it. So I'm not going to go over the applications problem. I'm just going to go over these basic graphing problems. So we'll look at example 8 for sure, and example 9. So in example 8, I like this one because we're going to go over the oblique situation. So we have an oblique asymptote. And we go through the same steps pretty much. Vertical asymptotes first. Vertical asymptotes happen in this case where x minus 1 is equal to 0, x equals to 1. And as long as that's not a shared factor in the top. So you look at the numerator. Numerator is x squared plus x. I'm going to set this equal to 0. We can factor out an x plus 1 is equal to 0, and we get x equals 0, x equals negative 1. And in this case, they don't share any common factors. And since they don't share any common factors, then I'm going to go ahead and say that that's the vertical asymptote. And I'm going to go ahead and draw a vertical asymptote at x equals to 1. So I kind of did 2 steps in one, because I'm checking to see whether or not that 0 in the denominator is actually a vertical asymptote. Because if that number 1 had showed up here in this set, then there's a problem. That's not going to be a vertical asymptote. That's going to be something else, more than likely a whole point discontinuity. So in this case, that is a vertical asymptote. And what I've already done, since I've checked to see if those 2 sets have anything in common, and they don't, I've also found the X intercepts. This one has 2 X intercepts, one at 0 and one at negative 1, which they're very, very close to each other. So one at 0, one at negative 1. And we'll see what goes on there. So we also have the X intercepts. X intercepts would be the third step after the second step. Second step is to find the other type of asymptote. Most of the time horizontal. In this case, it's not going to be horizontal. They've already told us it's oblique. So how do I check to see if this is an oblique asymptote? You compare the degrees. The degree on top, degree is equal to 2. The degree in the bottom is equal to 1. If the degree on top in the numerator is 1 larger than the one on the bottom, so we're not going to look at anything where we have a degree 2 larger or 3 larger or 4 larger, just the one where it's exactly 1 larger than the one on the bottom, so a degree of 2 and a degree of 1 in that order, top and bottom. So if the degree on top is 1 larger than the one on bottom, we have a linear slanted asymptote, which we also call oblique asymptotes. There's going to be an oblique asymptote, which I'll go ahead and call it. And then to find it, I'm going to have to use division. X minus 1, x squared, plus x, and then we divide. In order for those first terms to match, I need to multiply by x. That's going to give us a matching term of x squared, but that's also going to give us a minus x. We compare these two. we're going to be left over with 2x, it looks like. So then, that 2x is of the same degree as the divisor, x minus 1, so we keep on going. Once the remainder position contains a function that's of a degree smaller than the divisor, we stop. So in this case, we're not stopping yet. To match, we need a 2. That's going to give me a 2x and then minus 2. We compare them, and we have a difference of 4. And since the 4 has a degree 0, 1 smaller than the divisor, x minus 1, which has a degree 1, then we stop. So then we write the function f of x is the same as, in this case, 4 is the remainder. Actually, no. We write x plus 2, which is the quotient first. So quotient first, plus the remainder divided by the divisor, x minus 1. So it's as if we're drawing a linear function, x plus 2, and we're going to add in there this rational function. So we're mixing together a rational function, a simple rational function, and we're mixing that together with a linear function. So what ends up happening is something really, really weird. So the x plus 2 portion, which is the linear portion of it, this is going to be the oblique asymptote. And this is going to tell us what's happening close to the vertical asymptote, the x minus 1 portion. So that's going to curve out the stuff close to positive 1. That's the local stuff. And the oblique asymptote stuff, the x plus 2 stuff, that's going to tell us what that's doing out in the ends, towards the infinities. So what I'm going to do, in red, I'm going to draw the x plus 2 portion as an asymptote. So what you do is you graph y equals x plus 2. So the oblique asymptote, y equals x plus 2 is the oblique asymptote. So x plus 2, you know how to draw that. That's just a linear function, slope of 1, y-intercept 0, 2. And I kind of see what's going on now. So we can try to analyze using the calculator to see what's going on here. But what's going to end up happening is that there's a bit of a little hill, a maximum, and then this goes down this way, and this one goes this way towards the asymptote. Which that was poorly drawn. Not much better, but whatever. Then I got to figure out what's going on the other side. So just to prove my point, I can plot some more or find some more y coordinates for specific x coordinates. So let's say f of negative 2. So I get negative 2/3 when I plug in negative 2. Negative 2/3 is going to be below that line. If I plug in, let's say, negative 9. So I'm talking about something far out this way. So at x equals negative 9, I get negative 7.2. So negative 7.2 is down here. So that's pretty close. So it's going to be underneath that oblique asymptote line in that situation. So let's say if I get really, really close to 1. So if x is equal to 0.9, I get negative 17.1. So at 0.9, negative 17.1. So it's shooting down towards negative infinity that way. On the left, as x approaches negative infinity, then that curve approaches that straight line x equals, or y is equal to x plus 2. So what's going on the other side? Let's plot x equals to 2. So again, I'm using my calculator. So when x equals to 2, I get 6. Let's say x equals to 3. X equals to 3, I get 6 again. And that's kind of mirroring what's happening here. So something like that going on here. Oops. And then let's say when x equals to 6. When x equals to 6, I'm getting something around 8.4, somewhere around here. So it's doing this. It has a little bit of a minimum, then it goes this way, and then it jumps up towards infinity this way. And there's my graph for example 8. So we go in a particular order. Vertical asymptotes first. You set the denominator equal to 0. You also check the numerator to see if that's going to have any common zeros. And if there are no common zeros with the denominator, in the numerator, then whatever the zeros were in the vertical asymptotes, those are all, or for the denominator, those are all vertical asymptotes. So if you did it correctly to find the zeros of the numerator, those are also the x-intercepts as long as they're not shared with the denominator zeros. Then we worked out the oblique asymptote. We first observed that the degree in the polynomial numerator is going to be larger than the degree in the denominator polynomial, and they differ by a degree of 1. So one was 2, the other one was 1. The one on top is bigger, oblique asymptote. And you find the oblique asymptote, it's actually equal to the quotient when you divide. So everything that's in the quotient is your oblique asymptote. So that happened earlier in example, what was it, 6? In example 6, the quotient was 4, and 4 was the other asymptote, in this case the horizontal asymptote. So whatever comes out in your quotient when you're dividing will be your other asymptote, the non-vertical asymptote, so the other type. Now you can also check that with the first problem, number 5. If you did the long division, x minus 2 and x squared minus x minus 6, you'd get a quotient of 0 right away. That's a trivial case where you wouldn't divide those because the one on the bottom is bigger, but you'd automatically get a 0 in the quotient, and the 0 corresponds to the horizontal asymptote of y equals to 0. So example 9, which is the last one. So for example 9, f of x is equal to x squared minus x minus 6 over x minus 3. Immediately you see that the numerator degree is larger by 1. That one's equal to 2, this one's 1. This one's linear. So when they differ like that, we're more than likely going to see a oblique asymptote again. Maybe, maybe not. So what we do is we check for vertical asymptotes and x-intercepts. So vertical asymptote, x equals 3, it looks like. We set x minus 3 equal to 0, x equals to 3. That's a candidate as a vertical asymptote. Now we just check the x-intercepts to see that that number 3 doesn't show up in the set for x-intercepts also. So for x-intercepts, you set the numerator, x squared minus x minus 6 equal to 0. And I think we've already solved that one. No, that one is x plus 2 times x minus 3. Because if you take positive 2 and negative 3, you get negative 6 as a result when you multiply them. When you take positive 2 and negative 3 and you add them, you get negative 1. So I think that's the same thing as earlier. So an x plus 2, x minus 3 is equal to 0. You get x equals negative 2 as an x-intercept and positive 3. Problem is that positive 3 shows in both of those. So what that means is if I plug in x equals to 3 in the original function, f of 3 is going to equal to 0 divided by 0 is undefined. That's a problem. So no, there is no vertical asymptote, and that's not an x-intercept. So there is no vertical asymptote because the only candidate was 3, and it was found in the set of x-intercepts. So there is absolutely no vertical asymptote. So I'm going to say no vertical asymptote. And the only x-intercept is x equals negative 2. So I'm going to plot negative 2. So then what do I do? That's all I have so far. Maybe I can find a y-intercept. And you plug in 0 into the function. And if I plug in 0, you get positive 2, it looks like. Negative 6 divided by negative 3 is positive 2. And those are the only 2 points I have so far. In this case, we might want to give up. What do I do if I have no vertical asymptotes? That can throw us off. Well, what we do is we maybe do the division to see if I can gather any extra information. F of x, we take x squared minus x minus 6. And right now we're doing this in desperation. See if I can extract any information using the division process anyway, see what we get. Now if you remember, actually I don't even need the division process, do I? Because we factored the top. The top is factorable. F of x is equal x squared minus x minus 6 all divided by x minus 3, which in this case was x plus 2, x minus 3 all divided by x minus 3. And here it's obvious that you can see where that 0 divided by 0 situation is coming from. When x equals to 3, this is undefined. When x does not equal to 3 though, so let me say when x does not equal to 3, These two cancel each other out. Since we won't have a 0 divided by 0, we'll have something else divided by the same thing. Those divide out to 1, and you're left with x plus 2 when x does not equal to 3. So this is actually a piecewise defined function. This equals to x plus 2 whenever x does not equal to 3. And it's undefined when x equals to 3. So if you look at where it is defined, it's a straight line, x plus 2. But at x equals to 3, it has to be undefined. So what does that mean? And that's only at x equals to 3. So when x equals to 3, well, what would it have been if it wasn't undefined at x equals to 3? It would have been 5. There's going to be a hole there. Everywhere else it's defined, and there it has to be undefined. So it's a straight line with a hole at x equals to 3. Y would have equal to 5 in that case. So you'll have holes, the takeaway here, whenever the numerator and the denominator share a common factor. And because the only other factor that was left was linear, all I had to do at that point was draw a straight line. And that's going to go ahead and be it for the notes for 3.5 rational functions, which we've already done the homework for that, but hopefully this will help you review, which I'm going to be using quizzes from here this point on. Quizzes don't count for a grade in the UT gradebook, and in our class, quizzes counted for a grade for tests, but you should be aware by now, no more tests for the MHS gradebook. It's only going to be our daily or weekly assignments. And at the minimum, I'm supposed to have one weekly assignment from here on out until we go back to school, if we go back to school. So quizzes from now on will be unrestricted, unlimited. You get to see your answers right away. That's only as a tool for reviewing for the actual test. So there will be a test, and the test is going to be Canvas only. It's not going to have a handwritten portion. So it's going to be one 50-minute Canvas exam, from what I understand. More on that information later, or more information on that later. I'll have a date for us to get that done, which you're going to have to be able to do that on your own, at home, using your internet connection, your resources. So more on that later. But that's going to be it for this particular section. And then we'll continue with the next 5.2, which is limits, in the next video.